Share the screen. All right, so we should be sharing now and recording. Okay. All right, so hopefully the files download. Let's look. Again, these are, I guess they're still downloading. These are not considered big data by any means, but as you can see, they can be big. We had trouble with Sci-Fi 10, right? We couldn't get it to train fast enough for the 10 classes and also to learn well enough. Remember that for the challenge, you have to classify for all 10 classes, building your algorithm. Okay, so we're going to go ahead. I have these two files now, I believe, so I'm going to just move them. Guys are section 1. And they should go in here. All right, so hopefully you got the files. I'm going to show you a way. I thought about this a lot, and I just wrote like the simplest thing that I could think of to load the data. Okay, so it should be pretty easy to understand. And it loads fast enough, so there's not an issue. Speed. All right, so we can we don't need bright space anymore. Instead, we can go ahead and start writing our code, and we're going to implement a convolutional neural network. Remember, there's a lot of, not a lot, but there's some theory that goes with this, and I'm gonna do it after the code is done, just so that I'm pretty 100% sure that I can assign the homework today, the challenge. And it'll be due 2 weeks from today, which is that it might be the week of Thanksgiving, but it's not an issue with you guys because you are a Monday class. Any questions before we begin? Questions? All right, so let's add some of the code here. I'm going to, in the interest of not taking too much time, right? I'm going to just open the GitHub since the code is already posted there, and I will copy certain sections like the libraries itself, etc. So it's a lot easier to implement, right? So we can go ahead here. So go to the PyTorch repo in the GitHub, click on deep learning. We are done with MLP already. I already loaded the GANs code, so you can see that there, which is the next topic, probably, I'm hoping, next Monday. And then that just leaves one topic, which you should be really excited about, transformers, right? That's the thing that makes ChatGPT and all that stuff work. So we're going to build from scratch a tiny GPT. All right, so, but that's, the last topic. So let's go ahead here. I added this ITS 520 CNN's GAN, so you won't find anything here yet. But these scripts that I'm writing in class right now, when they're done, I'm going to load up there. Because in some of these folders, I have like a ton of files, and it might be confusing to you. But for now, I'm using this one as reference. And so this is the code, basically, that we're going to run. And so in the interest of speeding up, I'm going to just copy some of these things, not all of it. So we can copy the libraries, okay? All right, so the libraries are the same ones you've used throughout, right? Torch NN as NN, NumPy, Torch utils data for data set and data loaders, and then import pandas, random, NumPy, and of course matplotlib as PLT, and we've also used pill image. Okay, so we've used all of these libraries, and that's what we're going to use here as well. So go ahead and click on that. Okay. All right, let's let it load, and hopefully it won't error out. And then after that, because we're taking this object-oriented approach, which is what everybody does nowadays in deep learning, machine learning, I'm going to just keep with that approach. As you will probably appreciate it when we get to both GANs and transformers, which are much more complex algorithms, and therefore you'll see the advantages. Okay. So I want to get you to think that way. So if you remember, we used the function view to change shapes, etc. And so now I'm just going to create a little class of view, but it's basically the same thing. Okay, so we're going to go ahead and do class. And I'm going to call it view. And this will be helpful as GANs, you know, and other algorithms later on are going to require a lot of manipulation of images, etc. And so we're going to, it's basically for future classes. So we're going to here make use, as we have done already, and this should be familiar to you, the NN module, right? So basically we're doing class inheritance of the built-in PyTorch module, okay? NN.module. So then, as usual, we're going to have our init and our forward. So I'm going to do def. Remember, this is 2 underscores init. Okay. And then we're going to do self, comma, shape. So we can send the resizing shape. And then here, we're just going to have the initialize the inherited class by doing super. Okay. Dot underscore underscore init underscore underscore open parentheses, close parentheses, right? So we initialize that class, and then we just create a parameter called dot shape, and we pass to it the input variable shape. Right? This actually works very much like the built-in view function in tensors. All right, so we can do that. Then we add the forward, so I can do def forward self, comma, and then X would be the, as usual, the input tensor that we are passing, and then we are going to process it. So now we would just do return X dot view, which is the built-in function. So as you can see, it basically is the same, right? So view, and then we just pass to it the parameter self dot shape, as we would. All right, and then we create this little class for the view function, and then later on we could modify these a little bit. All right. The next thing I'm going to do is I'm also, in an object-oriented fashion, I'm going to create a data set class. And again, this is important. It's almost like we're doing the heavy lifting right now for future GAN algorithms where we need to visualize the images, right? The whole point is if we're going to do generative models, we want to generate images, view them, all that kind of thing. All right, so we're going to create a class now for the data set itself. We're going to call it MNIST data set. Okay. So let's go ahead and do that. So let's do class. Let's do class MNIST data set. Okay. And this is going to inherit the data set module that we just imported from Torch Utils data. I'm going to do data set colon. All right. And then this is basically, as I said, I kind of may not be the most optimal thing in the world, but it's clear enough. So that's kind of where I was going. All right. So this function is going to have, so this class is going to have 1, 2, 3, 4 functions. Okay. We're going to have 4 functions in here. So let's go ahead. The first one is the constructor, the init class. So I'm going to do def underscore underscore init underscore underscore, and then we're going to do self, comma, CSV file. So as the name implies, this is going to read in that MNIST train, MNIST test files that you have downloaded already from Brightspace. Okay, so click colon here. And then what do we need? We need a couple of things in this class. So let's do self.data_df. So the df, remember, stands for data frame. So we're reading in through pandas. So then I'm going to say pandas, dot read underscore CSV. Okay. So what do we read? We read CSV underscore file, comma, and then we do header equal. Guys, do you have a question over there? I can hear you all the way up here. All right, so we do data df, right? We're gonna do pandas dot read CSV, and then the name of the file, and then header none. That probably implies that we have a header in the first line. Remember, this is MNIST, so the images are 28 by 28, which means, you know, they would be 784 once we stretch them out. Okay. Yeah, please.
What are the other headers?
It's the header has, the header should be, it's a good question. There should be 785 columns, I believe. I think they're already stretched in that CSV. We'll see that in a sec. So if that's the case, each row should be one image, size 784, because it's 28 by 28. You guys remember how to make a 2D into a 1D. And then the last column, as you might imagine, should be the class. So the class is a 10 class data set where the classes are the digits. So it's handwritten digits. So one image is 7, another image is a 3. Got it? Yeah. All right. It's a classic. This is like a very famous data set. Okay. The classic MNIST data set. Jean Lacoune, I think, created it. All right. So now let's go ahead and what else do we want to do? What do we want to do? Yeah, let's do, we're going to create a few variables here. So we're going to do self labels. Okay, and this is just a list. So remember that PyTorch takes lists, right? So we're going to do self.labels. We're also going to do self.tensor IMGs. So we're going to have to convert our images into tensors, right? And we're going to actually have one-hot encoded version. So in labels, we have the integers such as 3, and you should know by now what a one-hot encoded vector means. So it would be a vector of size 10 where all the values are 0 except the one that corresponds to the label, which would be a 1. So we're going to call this one-hot classes, right? And that's going to also be a list. So we're just initializing these variables. We may come back to this later to modify some aspects of it if need be. All right, so we, again, just taking our object-oriented approach. We want to know maybe the number of samples. The number of samples in MNIST, I think, is 60,000, I believe. And then there should be 10,000 for the test set. So let's do self.n_samples. Okay. And we can calculate this value by simply doing something like length of self.data_df, our data frame. All right. So remember, we're reading through pandas CSV file, so it should become a data frame. All right, so we can have then a function. So we can have that variable. Yeah, let's leave it at that. Now, the next step is going to be to take all the samples and convert them into the one-hot encoded vector. We're going to convert it into tensors and all of that. So we're doing the conversion here. So I'm gonna create a new function, def convert. So I'm gonna do definition convert data to tensors. So convert data to tensors. Okay, I'm gonna do self colon. Okay, so this is basically where we proceed to just grab every row in the data set and process. Okay, so I'm gonna do here for index in range of, and then I know the size, so I'm just gonna do self dot n samples just like that probably. Okay, and now we're gonna iterate through my pandas data frame and just convert the data. Okay, so the first thing I want to do is get the label. So I'm gonna say label equal self dot data df, and then we can use an option called iloc to really reference the rows. You know, like if we're grabbing each row, we're gonna index and grab whatever we want. So it's important to know that we'll look at the pandas data frame, but it's the labels should be in the first column, right? So then we're gonna say quite simply index comma 0. And that way we can grab the label that we need. Does that make sense, guys? Any questions? It's a classic for loop here. All right, so next step will be to create the one-hot encoded vector. So I'm just going to say target equal torch dot zeros. So I'm creating a tensor of zeros. And then I'm going to say that I want it to be of size 10. This is going to be my one-hot encoded vector. Okay, so now all I need to do is change one of the values to 1 that corresponds to the label. So we can do that by doing target. And then we're going to say int label. And that's the index. And so that value is assigned 1.0. And all the other values should be what? Should be zeros. Is this clear for everyone, guys? So we're doing the one-hot encoding as we had discussed previously. The next step then is to convert the image into a torch tensor, right? So we're going to do in the same function image values, okay? Image values equal torch dot float tensor. We're converting it into a torch float tensor. Okay, so we're gonna plug in here, same idea. We're gonna do self dot data underscore df dot iloc, and then we can do index, right? Yeah, because that's I'm iterating through index, and then I do 1 colon. What does that mean? Yeah, right. Good. All right, so you should know that, right? And then obviously this is still an object, so we need to grab the values from there. So we're going to do values, and then we're going to read them in as type float. Okay, and then once that's done, we've got a tensor. Okay, we've got a tensor. Because these the pixel values go from 0 to 255, we can easily normalize this by just dividing by 255. And so that's and remember, in machine learning, it is always recommended that you normalize the values. Certainly for the SciFar 10, figure out ways of normalizing. Is this clear, guys? Pretty simple, really. And then finally, once we've done this, now we can load all of our data into these lists that we created conveniently so that we can use it later on. Okay, so we're gonna go ahead and do that. So I'm gonna do self dot labels dot append, and I'm going to add in here the label. Okay, then the next one is going to be self dot tensor imgs dot append, right? And I'm going to add in here my image values. And then the last one should be self dot one hot classes dot append, bless you, and then this is going to be target, which is the one hot encoded version of my data. Okay, so I just want it to be a little bit clear to read. All right. Now, the next function that I want to create is a function so I can display the image and the labels. Okay, so I want to display it. So let's go ahead and define a function. We're going to do here define plot image. Okay. So it's basically our own functions. We're going to do self, comma, index, and that way we can just pick any index that we want from our data set and display it, okay? So we're going to go ahead and grab the image. So we do img and then self dot data df dot iloc. And then we're going to say index, comma, and again, it's the image, so it's 1 colon, then dot values, and then dot reshape. So this should tell us something quite important. This tells us already that the images are already a vector, right? So they're already 784, and we are reshaping them to be 28 by 28 so that we can actually visualize them. Is that clear? All right, then we can go ahead and add things like print. You want img shape, right? So you want to look at the shape, confirm. You might want to look at the label of it. So then you can say img, or sorry, we're going to make this a string. And we grab this from the same place, self data df dot iloc, and we're going to do index, whichever index we want, and we grab :0. Okay, so that gives us the label. It's now a string, and then we can take the image, make sure the type is float, so img dot as type float. Okay, and the last part, of course, we return img and label itself. All right, and that way this function will help make things easier for us to get our image and our label. All right, so let's go ahead and see if all of this works. So I'm gonna go ahead and run the class. Okay, so no errors, that's good. Now let's load our data set into this class. So we can start building an architecture. So I'm gonna do MNIST data set train. And I'm going to invoke MNIST data set. And I'm gonna look, it takes the file. So my file is in the same place. So it's just gonna be MNIST train dot CSV. Everyone with me? So once you do that, go ahead and run this and see what happens. Okay, so that looks like a good sign. Okay, so I got the same message. So should have loaded the data set. Okay. All right, so now let's go ahead and print one or load one of the images. So I can do my IMG, comma, label, MNIST train. No, sorry, MNIST data set underscore train. Okay. So we have the function now, plot image, right? So I'm going to use that one to load the actual image. So I'm going to say plot image, and that takes as input the index that you want. So it should be, let's say 117. Let's run that one. Okay. And we got an image. It printed that the shape is 28 by 28. So that should have worked. All right. So now what we want to do is, visualize that image. We also want to visualize our data set itself. So to do that, we should be able to just invoke the variable. Let's do MNIST data set underscore train. And then dot data underscore df, which is the data frame in that object. So let's go ahead, save it and run it. Okay, and there it is. Now notice this one has still the headings, right? So it actually still has those in. So we're gonna not need to remove those. Okay. So to remove that, let's go to the here, read CSV, and let's do self dot data df equal self dot data underscore df dot drop, and we're gonna drop so we're gonna use this function labels, and we're just gonna indicate that it's probably 0, the first one. Okay. On the axis 0. So the rows. Okay, so I'm going to say axis 0. Okay, so of the rows, get rid of 0. Don't get rid of columns, get rid of rows. So now this should work, I believe. Let's run it again. Run this one again, run that one again. All right, it's processing. Let's give it a minute. Okay, good. So you can see we want to get rid of this 0 here. So I'm going to hit run again, and it should be gone, right? Questions? Make sense? All right, great. So we loaded the data frame. Now we want to look at the image. We want to see what these handwritten digits look like. Okay, so we can use matplot. I'm going to go ahead and do plt.show my image, my IMG. And then I'm going to do plt.show. And then I'm going to do print label, which I also have. Okay, so let's go ahead and run this and see if it works. Okay. What number is that? According to the labels, it's a 2, and I believe it is 2. Now, it looks like it's in color, but it's not in color. It's just Matplot is actually making it to look like this, but it's not in color. Okay, got it? So it just looks nicer, but it's still black and white. So there's only one channel, not 3. All right, any questions so far? All right, so now that we have this, we are ready to convert the data, right? We've loaded it, but we haven't converted it to tensors and all that. That's the function that we define here, convert data to tensors. So this for loop, basically, we want to run. So we're going to run it down here. Should be straightforward to do. We're going to invoke MNIST dataset train again. MNIST dataset train dot, and then we're just going to say convert data to tensors. So convert data to tensors, and that should do basically the conversion. So I'm going to hit save, hit run. Okay, and it's doing that. And now, believe it or not, all we have left is to define the architecture, and then we can start processing. Okay, so it should be. Remember, I'll go over the theory of how CNNs work. After this, I just want to get the code running so that you guys can start working on the assignment. Yeah. Yeah. This one? Yep. All right, so let's give it a minute to finish converting. And then the next step is going to be to define our classifier. Which we're going to look at an even more detailed way of writing the architecture. Okay, so let's go ahead and start defining it. So we're going to create a new class here. Okay, and we're going to define, this is another approach where you define everything in the class. So I'm going to do class classifier. Remember, this is really a CNN classifier, so maybe I'll just do CNN. Okay, classifier CNN. Okay, this will inherit the nn.module. Okay, then I'm going to do define underscore underscore init underscore underscore. So again, I'm just initializing the inherited class in this constructor. So I'm going to do self. Okay, so here we do super dot init like that. Okay, so initialize the inherited class, and then we're gonna define the architecture. So I'm actually going to do the architecture last. So for now, I'm just gonna write this. So I'm gonna do define the CNN architecture. Okay. And so we're gonna have an object in here. And the object should be self dot model nn dot sequential. Okay. Like that. And now we're gonna define in here the architecture for our CNN. Okay, so I'm just gonna do this. And we'll come back to it. Okay. So the next step is here we can define several things already. So we're going to define the loss function. So I'm going to add create loss function. Okay, so I'm going to create an object self dot loss function. Okay. And we're going to look for a function, a loss function. So this yeah, so we're gonna have to pick a cross entropy loss. So let's just plug in one for now, okay? So let's just plug in BCE loss. We can change this at any time, as you remember. I think we've used a different one in the other model. Okay, but let's add that in. And then we're gonna also initialize the optimizer. So it's just gonna be self dot optimizer equal torch dot optim dot, and we're going to use the atom optimizer. So this will take, since we are inheriting this class, we can reference the parameters simply by saying self parameters. Okay. Got it? So the same thing we've done before. We'll define the learning rate at some other point. All right, a couple of things more that we're gonna need. We're gonna have a function that allows us to print progress of the loss function, but now we're gonna print it. This will be very useful when we look at the GANs because we have a couple of losses there, and we want to actually those losses give you information about the GANs. So again, I'm gonna just code this up already. So we're just gonna say we're gonna create the parameters for that. So I'm gonna add a comment here. I'm just gonna say the counter and accumulator for progress. Okay, so it's just a couple of variables, self dot counter, and this obviously is going to be 0, and then we're going to have self dot progress, which what you usually do is create a list, and then this list is going to have all the values so that you can plot them basically later on, and this is very useful. Okay. All right, so that's that part. That's basically the constructor, the initialization. The next step is in this class, we're going to have everything, the forward function, the train function, and even a plot function. So let's do forward. So this is gonna be define forward, which will take self comma inputs, which is the X, basically the input image or whatever it is. So we run the model basically. So I'm gonna do return self dot model. What is self dot model? It should be this object, right? So self dot model, we run it. So obviously to run, we have to provide inputs in here. Got it? All right. And then now we're gonna build the train function. And that'll just make a lot of this a little bit easier. So there, like I said, there's a lot of ways of doing this, and you guys, I leave it to you if you'd like to make it better, all right? But this should work, and it's simple enough to understand. All right, so let's do the train function. So this is really the bulk of it. So let's do define train self, comma, inputs, comma, targets, okay? So this implies that we're giving it the input image and the labels, basically. So we would calculate in this approach the outputs. So that's going to be self dot forward inputs. And then we're going to calculate the loss. So that's going to be self dot loss function. And we're going to do outputs, comma, targets. Okay. So it's the same thing we've done before. And this part is just for the progress bar. As I said, this is going to be important going forward. So we are going to do self dot counter. So, you know, the classic notation plus equal 1. And now we're not going to load every loss. We're only going to load losses every 10 iterations, okay? So basically then I'm going to do if self dot counter modulus operation, this should be a percentage sign. So that's the mod in Python, 10 equal 0, right? So this means every 10, it's going to load up the value, okay? In the for loop, in the iteration. So this implies that there's going to be some kind of a for loop. All right. So if the condition is met, then we are going to add it. So we're going to do self dot progress dot append, and we're going to add in here loss dot item. Okay, so the loss is this value over here, and so we're adding it so that we can plot it. If this is just so that we can track how many epochs have, or how many samples have been trained. So we're going to do self dot counter, again mod, but this time 1,000 or 10,000. Yeah, 10,000. So only every 10,000 are we going to print the value. So it just goes a little bit faster. Also, we don't want the Jupyter to have 60,000 printouts, right? Which it could. So we're going to do equals 0. colon. And then now we just print it. So I'm going to do print, double quotes here, counter equal. And then we're going to do comma here and self dot counter. Okay, so we're going to print out the counter so that we can keep track. All right, once we do that, then obviously we do the magic of PyTorch that you should all be familiar with. We're gonna perform backward, zero grad and all that. So I'm gonna do self dot optimizer dot zero grad, as you said, yeah. Zero grad, zero out, and then loss backward to calculate the gradients. And then self dot optimizer dot step. So the exact same thing that's so familiar already. And that basically should do the training. So once we've completed that part, we want to have now a function that plots our losses, right? So we want to have a nice handy function. So we're going to have it also in this class. So I'm going to do define plot progress underscore progress. Hopefully we'll be able to reuse some of this code because we'll be using MNIST for GANs next week. And it should hopefully be easier. All right, so plot progress again, self. And then we're going to do df pandas dot data frame. And this is going to take as input the self dot progress. And we're going to say that the columns are going to be called. We're creating a pandas data frame here. And we're going to say that the name of the column will be lost. Okay. All right, remember, this is just for presentation, for viewing the losses. Okay. So now we're going to just plot it. And actually, we're almost done, right? So df plot, we're going to specify the values. So we're going to say in the y-axis, y lim equal from 0 to 1. Okay, and then the figure size is going to be 16,8. And then just let's add this alpha equals 0.1. Presentation, the marker is going to be a dot, comma, grid equal true, and we also want some y ticks in the chart. So we're going to say 0, 0.25, 0.5. This is just for presentation. Okay, so the chart looks a certain way. And that should be it, hopefully. So we're using the data frame function to plot, basically. All right. So that should be it. And now we still need to finish the architecture. I haven't done that. Okay. And then we're gonna run it in a loop, and that's it. And that trains it. Okay. So as you can see, I haven't done anything that we haven't done before. Okay. The new thing that I'm doing now today is that instead of using a classic deep neural network or an MLP, now we're going to do a CNN. Okay, that's basically what we're going to do. And I'm also going to throw in some functions that help out just performance, basically. All right, so we're going to then, that means I'm going to save it actually. And I'm going to go here to NN sequential, and this is where I'm going to add the CNN architecture. Okay, so I haven't discussed the CNN yet, but basically, whereas in a deep neural network, you have your inputs, your outputs, and then hidden layers, right? In a CNN, you have inputs and outputs, and you can have hidden layers, but you can also have a new type of layer called a convolutional layer. And so we're gonna explore what that is in a second when we look at the theory. But in essence, think of it this way. You have an input and an output, and it goes through the convolutional layer, which does something to it to transform it, okay? So that's basically the idea. So the implementation of this is pretty much the same thing. You do something like nn dot con 2D, and that is the CNN. Okay, we can look up conv 2D. Online, which is what I recommend you always do with these types of functions, and read the definition of it. There's going to be various options there. So it's a class torch.nn con2d. It takes the number of channels, the number of input channels, so that would be RGB or black and white, the number of output channels, which relates to the filters, the size of the filter, the stride. So it applies a 2D convolution over an input signal, and that's it, right? Composed of several planes. So as I said, we're going to look at that theory in a second, but think of it as a function, takes an input, the image, and it processes it to create an output image. How it does that is what is called a convolution, all right? And we will explore that in a second. Any questions? So that's basically the idea. All right, so let's keep implementing this. So I'm going to have conv2d. This part is really important, okay? This is the channels. So in your case, you have one channel because it's black and white. But if you had color images, then you would have to address that. So here, the value is 1 to indicate the number of channels, okay, guys? Black and white. Then after that, you're basically saying how many outputs I have. So I'm going to say 10. You can say any number that you want. Just keep in mind that this is going to affect the outputs, okay? So here I'm saying that I'm going to create 10 filters. And each one of those filters is going to take that input image and modify it. So that means that the input image that, that is one image through 10 filters produces 10 output images, okay? And so that's the idea. So that's part of the architecture. Then you can say kernel size, kernel underscore size, and that's going to be 5. What does that mean? It means my images are of size 28 by 28. The filters that I'm applying are of size 5 by 5. Okay. And then there's something called a stride, which is basically like how it moves across the image. So I'm going to say 2, you can say 1, etc. So it does every pixel or it does every other pixel and so on. Okay, and that's basically it. So we will come back to this, as I said, in a sec with another example of how this can work. But for now, I just want to show you the basic architecture of the convolutional neural network. After that, we can do another convolution. So just like we had done before in other approaches. So we're going to do NN conv 2D. And now, because we have 10 outputs from the previous one, we can say 10 here. And then this is 10. Okay, so you define it, basically. Now I'm going to say that I want the kernel size to be 3 instead of 5. And remember, this is part of the architecture, so I can say as I want it to be, okay? And the stride, I'm going to keep it 2. Okay? And finally then, you are going to have the last layer is usually a regular hidden layer, as we have known before. So then you can say nn.linear. And then we're going to define a value here. And then this is the last one, which should be 10. Okay, that's the number of classes, because it is MNIST. In this case, I can use softmax or sigmoid, so I'm just going to use sigmoid for now. Right? Do you guys see that? Does it make sense? It's the similar approach as we've done before, except that now instead of just using regular linear functions, or I'm missing an I. Instead of using regular linear layers, right, the ones that we have used before, we use convolutional layers, which are a little bit more involved, but it's passing from one to the other. Now, there's a few efficiencies that we can add, that we need to add. So we're going to add activations here, just like we did ReLU before, except I'm going to do something called the leaky ReLU. Okay, and it's I think it's a methodology to maybe I don't remember exactly what the leaky ReLU does, but it adjusts the ReLU, or it sometimes doesn't apply it, basically. So again, we can look it up. So I'm going to do leaky ReLU here, and it takes a value 0.2. So you can modify it. And then there's another technique. Oh, and I'm forgetting all the commas. So this should... Now, there's another thing that has been invented, basically. Just like I think at some point I added something called dropout, and dropout was supposed to maybe improve things. There's another technique that has been invented called batch normalization. And what batch normalization is going to do is it's going to try to normalize not just the inputs now, but once something comes out of the hidden layer, of one layer, it normalizes the data. So every layer you can normalize. And these are things that can give you good results. So if you don't like it, just comment it out, okay? The ReLU needs to be there to be a neural network, right? But the batch normalization is just a technique that, in general, has been found to improve results. This is definitely done in transformers, right? And these are little things that really improve. So transformers have a ton of these. Transformers have something called a residual, and you'll see it's kind of like a little add-on that addresses some problem. Okay, so we'll talk about that when we get to transformers, but for now, we're going to do batch norm. So basically, another thing is, as the name implies, when we did normalization before, we do it over the whole data set, right? This is a normalization just over the batch that it's training. Okay, so batch norm, and then this is going to be 2D. Okay, so okay, and it's going to have the value 10 correspond to the ones we've already done. And then we're going to repeat this here in the next layer as well, which would be here. add a comma there, and copy these here. Again, with the batch normalizations, you can always just do that. Remember that these are just a whole bunch of techniques that in combination could give you the overall best results. Okay? All right, but I'll leave them in. All right, so we are almost there. This one, remember, the previous ones are convolutional layers. So I'll say first CNN layer. Okay, that's the one with the normalizations. This is the second CNN layer. And then the last one is what? This is a simple feed forward layer, okay? Which is what you have done in other architectures. Just this is what the normal layer is called. It's called a feed forward layer. All right, so that should be it. We got to figure out this value, and I'll show you guys a technique. Remind me to calculate these. These are very important. Whenever you have a different size images and you start applying things, the outputs change. And so you want to be able to print out this to kind of figure out the values. I already figured out that the value is 250. But I'll show you guys how to calculate this. The idea being that that's what came out, okay? So you had an image, you run 10 filters through it, passes to the next layer, and then another 10 filters. But there's also a thing called max spooling that is actually cutting the images in half. So like initially an image might be 28 by 28, but it's not going to be 28 by 28 in the end. The CNN by definition tries to make them smaller and smaller. Okay. So this is a thing that I expect on the Sci-Far 10 to maybe give you trouble. Okay. So I want you guys to figure this one out. All right. But as I said, I will give you some code that is in the GAN stuff that should help you out. All right. For this one, for this to run, I'm just going to leave it at 250, which is the value. All right. And I think that should be it. So now we should be able to run this one. So let's add, now we can actually run this cell and load the definition of this class. So no errors, good. Now we can go over here and let's just train, all right? Since we've done everything pretty much in the, class, we have very little code to write. So let's do, I think if we write it in these Jupiters, if we write percentage time, the cell will give us how long it took to train. So that might be useful. So let's try it. Okay. And now create the class. So C, you can call it CNN equal classifier. What was the name of it? Classifier CNN. Yeah, classifier CNN. Underscore, yes. Classifier CNN. So there we go. We've instantiated our entire CNN object. And now we're going to decide the number of epochs. So I'm just going to do 3 for the sake of this running fast. You can do more, of course. Now we do the loop. So for I in range, epochs. And then we're going to print training epoch. Okay. Comma, I+1 of epochs. Okay, so now for I in range, as I said, this is not like the best code, but it's clear enough. All right, so it should run okay. So where do we have, we know the number of samples because we have that in the class, in the object, right? So we do MNIST dataset underscore train dot n samples. Okay, so we're gonna iterate. Oh, don't forget the colon at the end. And now we're almost done. We're gonna do label. We're gonna grab it directly from MNIST dataset, which is already, everything is already processed. Notice I'm not creating a data loader for this one. You guys can do that if you'd like. You already know how to do that. So MNIST dataset underscore train, and then we grab from labels I, right? And then we can repeat this for image tensor. So image data tensor. So I'm going to do MNIST dataset train dot tensor imgs I, and then finally target underscore tensor MNIST dataset dot one hot underscore classes. Right? That should be correct. So let's just make it a little bit more line here. Yeah, I mean, not the greatest. You guys can make it better. All right, so now that I have this, I have my data and I have one thing left to train, right? So I'm gonna call my class C dot, oh no, I called it CNN dot train. So notice that I'm not training in batches either, right? I'm just giving it one image at a time. You guys can try batches. Go ahead, please. So the batch normalization probably won't do anything here, right? So play with it. All right, so train takes the image and the label, right? But it takes the one hot encoded tensor, right? Not the label itself. So then we can do train. Oh, sorry. We do the image. So image data tensor dot view. And this view is for reshaping, right? So we got to take the image. Now keep in mind, this is interesting. When we were doing a regular neural network, we would have an image that was 28 by 28 and we would spaghettify it, right? If you remember. Now we're going to do the opposite of that. We have images that are already a vector, but a CNN wants an image. So we're going to unspaghettify. All right, so I'm going to do in view 1, 1, 28, 28. Does that make sense, guys? What is 1 here? The batch of 1. What is this number? The channel. So if you have cipher 10, this might be a 3. I don't know. You figure it out, right? But that's going to be one of the challenges when you implement the CNN on cipher 10. Okay? And also the dimension, but I will give you some code for that as well. So remember, I want this homework to be a little bit more challenging. It's not that much more difficult, but I think enough for you guys to step it up. All right, and that should be it. So now we're gonna go ahead and run the training loop. All right, so if you guys don't see any errors, let's go ahead and try it. Ah, there's an error. That's great. BC losses. Did I not define it? What I did? Oh, it's, yeah. NN. Sorry. Okay. NN. You guys see my error? I don't know if that's a lowercase. Try that. All right. So it should be an uppercase L. So let's try it again. Ah, okay. So I'm missing this underscore as well. All right, one more time. Okay, there we go. So it's training. Okay. 5 by 5. Probably in the architecture. Oh, yes. Okay. I know what happened. You guys will get, I think, if I do the following, you'll understand. What does that do? What does that do? I added this, right? It gave me an error and I added this. All right, so let's run it first. Let's see if it works. Nope. Yeah. This is because the images, I'm just spaghettifying it into a 250 because this one is a vector of 250. So this should have worked. Can you guys try running it? Mine is kind of stuck here. Guys, can you try running it? Okay. So argument after must be an iterable, not int. Huh? Says it's the forward.
It's from view class. We should find it.
Is the view one? I don't get that error actually. Still giving me an error. Okay, this is a different error. Classifier CNN object has no attribute progress. Progress. Okay. Sorry about that one. Progress. Okay. Let's try this again. Can you guys try it also? Let me know if it runs for you. Is it running for you? It is running for you? Huh? Okay. Did it finish?
First contract just hit 10,000.
10,000, okay.
Like,
Yours finished? Okay. So then it means it's trained, right? That's what that should mean.
but I do have this error.
Oh, so it's giving you an error then.
So that part's fine. Earlier though, the PLC I have to show.
Mhm.
So those my equipment for some reason.
Yeah, that's when that happens. I've noticed that it's like installation issues. Like you have one dependency, and matplotlib can be mean to you when you install it sometimes. So maybe try creating a new environment just with these libraries and see if that helps. How about the rest of you guys? Is it training? Mine is still stuck.
What is that comma you shape from?
Yeah, that comma, I had it in my code originally, and when I was writing it, I took it out because I thought there's no reason for this. I put it in just to try, and I mean, I don't know honestly. The shape is a variable. Maybe it puts it in view as a comma. Imagine like 3 comma in the actual view, but to indicate that there isn't just one value, but at least one and more. So it maybe doesn't want just one. Maybe it wants at least one and a comma. That might be it. So you can test that, like here in this train one, right? Putting in just, it wants probably one and at least -1. You know what I mean? But it doesn't want just, although -1. No, because the first one is the batch, so you wouldn't. It would be batch, comma, and the vector. So I think that's what it is. It requires a comma there so that there's one is batch n and then the vector. So that's kind of what I'm thinking right now. All right, so mine's at 10,000. Okay, guys, so at 6:30, let's let this train for a while. And we can take our break from 6:30 to 6:40. And then hopefully it'll be done by 6:40 magically. And then we can finish it up. But actually, we've done a lot of it already. And then we can get into the theory of how CNNs work. But you see the idea. So we'll finish it up. As I said, this lecture actually involves things that I'm going to need in Gann's lecture. And so this is why a lot of it is written the way that it's written. But yeah, so let's take a 10-minute break. I'll stop the video. I'll take attendance at the end of class today. So let me do stop. And I'm going to do stop recording.